Assalamualaikum everyone. I am Dr. Ayesha Siddika Shammi, lecturer of Physiology at Bashundhara Ad-din Medical College and Hospital. So today we are going to learn the membrane potential. So what is membrane potential? The electrochemical changes or the electrical potential difference across the membrane is called membrane potential. So this electrical potential exists across the membrane of all cells of our body. But there are some cells of our body or some tissues of our body that can generate rapidly changing electrical potential or electrical impulse that transmit across their membrane. Now the question is, what are those excitable tissues? These excitable tissues are nerve and muscle tissues are excitable tissues. These tissues can generate rapidly changing electrical potential that is called action potential. Now, the membrane potential has two conditions. One is resting membrane potential . Another is action potential. Okay. What is resting membrane potential? The membrane potential at resting stage is called resting membrane potential. This is expressed as negative. Why it is expressed as negative? Because inside of our cell is negative. Inside of our cell is negatively charged. Here I have already written some resting membrane potential of different cells. This chart is taken from Guyton. This is 14th edition of International Guyton. So here we can see in neuron the resting membrane potential is -60 to -70 millivolt. In large nerve fiber it is -90 millivolt. In cardiac muscle it is -80 to -90 millivolt. In skeletal muscle it is -85 to -95 millivolt, and in SA node it is -55 to -60 millivolt. Now the question is how the resting membrane potential is generated or how the resting membrane potential is maintained. So say in a large nerve fiber the resting membrane potential is -90 millivolt. So how this -90 millivolt is generated? This -90 millivolt or resting membrane potential in large nerve fiber is maintained by three factors. Number one is contribution of potassium diffusion potential. Number two is contribution of sodium diffusion potential. Number three is sodium potassium pump. Now let's learn the topic or let's learn the conditions one by one. At first let's learn potassium diffusion potential, contribution of potassium diffusion potential. We know potassium gradient or potassium concentration in ECF is 4 milli equivalent per liter. In ICF, potassium concentration or potassium gradient is 140 milli equivalent per liter. So potassium concentration is more in ICF than ECF. So the ratio is from inside to outside, the ratio is 35:1. So now the question is how the negativity or how the resting membrane potential is generated by the contribution of potassium diffusion. So we know the potassium is very much permeable. Potassium is 100 times more permeable than sodium. So inside of our cell, potassium is more. When the permeability increases, membrane permeability increases, potassium diffuses from inside to outside of the cell. Okay, so the positive ions or positive charge is carried out from inside to outside. So inside of the cell, the negativity is increasing. So, but this is continuing. So within 1 millisecond, the potential difference inside and outside of the cell is called diffusion potential. So this potassium diffusion occurs by potassium leak channel. So this diffusion potential we can calculate it by using Nernst potential or Nernst equation. By Nernst equation, the equation is EMF or electromotive force is of potassium. Let's write here potassium is equal to plus minus 61 log concentration inside divided by concentration outside. There is plus minus or positive negative, but for positively charged ion this sign will be negative. So this is minus 61 log, concentration inside was 140, concentration outside was 4. So minus 61 log, this is 35. Minus 61 log 35 is 1.54. Okay. So it is minus 94 millivolt. So potassium diffusion potential by using Nernst equation is minus 94 millivolt. Let's write it down in a corner. Minus 94 millivolt. Now contribution of sodium diffusion potential. Number 2 is contribution of sodium diffusion potential. We know in the ECF, sodium is more, that is 142, and potassium and ICF it is 14. By potassium sodium leaky channel, this sodium will enter into the cell. So positivity is increasing. Let's calculate it by using the Nernst potential. Here it is log 14 by 142. So it is log 0.1. Log 0.1 is minus 1. So it is plus 61 millivolt. Potassium is plus 61 millivolt. But this summated potential by using Goldman equation or by Goldman equation, the summated potential will be minus 86 millivolt. Now let's come to sodium potassium pump. Contribution of sodium potassium pump. What is sodium potassium pump? Sodium potassium pump is an electrogenic pump which pumps 3 sodium from inside to the outside of the cell and 2 potassium from outside to the inside of the cell. So more positive ion, that is 3 sodium ion is going outside and 2 potassium ion is coming inside. So there is potassium, more positive ion is lost. So inside of the cell it will be negative. So contribution of sodium potassium pump. So sodium potassium pump will form additional minus 4 millivolt. So net potential is minus 90 millivolt. That is how resting membrane potential of large nerve fiber is generated or maintained, that is minus 90 millivolt. Now let's come to the topic action potential. What is action potential? Alteration of resting membrane potential is called action potential, or rapidly changes in electrical potential across the membrane that transmit impulse throughout the membrane. That is called action potential. And what are the importance of action potential? Importance of action potential is for conduction of nerve impulse, for conduction of muscle impulse, then for other functions like function of macrophage, movement of cilia, secretion of glandular cell. This type of things is done by action potential. What are the stages of action potential? Stages of action potential are resting membrane potential, then depolarization and repolarization. Okay, now let's understand these three stages by drawing a figure. I am drawing action potential of large nerve fiber. So here the minus 90 is the resting membrane potential for large nerve fiber. So this line I have drawn, this is the resting membrane potential of large nerve fiber. This one is 0 and above this is positive. In this part we are showing millivolt and this way we are showing millisecond. So from the minus 90 millivolt, I am drawing this figure at first, then I will describe it. Okay. So this portion is resting membrane potential. From the resting membrane potential, this upward direction, this one is depolarization. This part is depolarization. This portion is repolarization. This is overshoot, or this portion is called spike potential. Okay. What happened in depolarization? That alteration of resting membrane potential, here alteration of resting membrane potential will occur. What occurs? It is negative. When the positivity increases, it becomes depolarized. So how depolarization occur? Depolarization occur here. To learn depolarization, repolarization, we have to know two channels. One is voltage gated sodium channel. Another is voltage gated potassium channel. When voltage gated sodium channel opens, there is influx of sodium ion. Influx of sodium ion inside the cell. So influx of sodium ion will increase the positive charge inside the cell, or across the membrane it will increase the positive charge. When the positive charge is increasing inside, so from negative it will go upward towards positive. Then when the voltage gated potassium channel closes, then when the voltage gated sodium channel closes, then voltage gated potassium channel will open. And what happened? Potassium efflux will occur. Potassium efflux means potassium will go outside of the cell. So there will be potassium efflux. By potassium efflux, repolarization occur. So we can say repolarization is re-establishment of resting membrane potential. That means when potassium efflux occurs, that means positive charges are going outside, so negativity is increasing inside. So this line will go down. That means negativity is increasing. By this way, when it comes to the resting membrane potential, that is minus 90 millivolt, so it comes to again the resting stage. Okay, this portion is called overshoot. What is overshoot? In isoelectric, after reaching isoelectric point, when the curve goes above 0, this portion is called overshoot. And I have written here spike potential, rapid depolarization and followed by rapid repolarization. At this point, this is called spike potential. And there is another term, it is not a stage of action potential, that is another term when the resting membrane potential, when the curve goes or resting beyond the resting membrane potential, it is called hyperpolarization. How hyperpolarization occur? When the voltage gated potassium channel is slower to close. When the voltage gated potassium channel remains open for a longer period, then the membrane become more negative and this line will go beyond the resting membrane potential. This one is resting membrane potential, this is going beyond resting membrane potential. This is hyperpolarization. But in some cases, here there is delayed, this portion, this depolarization portion or depolarization process will be longer and it will form plateau. This plateau occur in cardiac muscle. These things happens by two channels. One is fast sodium channel, another is slow calcium sodium channel. So here depolarization is occurring by fast sodium channel, and this prolongation of depolarization and this slow opening of calcium sodium channel is causing this plateau portion. Okay, for cardiac muscle I am writing here minus 80 or minus 85. Say it's minus 85. So this depolarization will occur by fast sodium channel, but it is slower to close. The fast sodium channel is slower to close. So, and slow opening of calcium sodium channel will cause this portion to prolong. This depolarization portion to prolong and cause plateau. And after that, by voltage gated potassium channel, repolarization will again occur. After repolarization, it will come to the resting membrane potential. So, where plateau occurs? Plateau occurs in cardiac muscle. It takes 0.2 to 0.3 seconds. Okay. So, in this class, we have learned what is membrane potential, what is resting membrane potential, how resting membrane potential is generated, what is action potential, importance of action potential. We have also learned by two graphs, that is, one is action potential of large nerve fiber and action potential of cardiac muscle, and we have also learned what is plateau, what is depolarization, what is repolarization, what is a spike potential, what is hyperpolarization. So this action potential is very important for our body. I have already mentioned it because it is important for conduction of nerve impulse, muscle impulse, and other functions like movement of cilia, secretion of some glandular cells, and function of macrophage. So this action potential is very important for this undergraduate level for student of first year, because if we don't understand action potential now, then in the later period when we will do post graduation and this kind of thing, will not understand a thing. So understanding this action potential is very important. So today's class, this is up to this. I have tried to show action potential in very summarized way, in very brief. I hope you understand. So up to this, it is for today. No more today. Assalamu alaikum.